So let me give an example. This is the formula that we're going to be using. So what we have to do in a specific example is figure out what the radius function is as a function of theta, and we have to figure out what the two radial angles to begin and with and end with are going to be. So let's have a look at one petal of the rose for cosine of 3 theta. Now you may remember this is going to be a 3-petal rose, so it's going to look like that. For simplicity, we're going to take the petal which is closest to the x-axis, in fact the one which is on the x-axis. So what we want to compute is what is the area of this particular petal. Now one thing that we can do, and that often happens when we're dealing with this kind of polar curves, we can use symmetry. You know that this curve is going to be symmetric around the x-axis, so what we can do is we can use symmetry and say, alright, what we're looking at is just twice as much as the area of half of that region. This is only going to simplify our computation minimally in this particular case, but it may end up simplifying things more later. So our area is going to be twice what? Well, twice the area of this polar region. So what we have to do is we have to now use the formula. The formula says 1/2, all right, so that's just a 1/2, which is nicely going to simplify with the 2 in front. Fine, great, not a big deal. And then integral between what and what. Let's look at the two limits. Notice that we're starting this region on the x-axis, and that's where polar curves always start. Or we start with on the x-axis where theta is going to be equal to 0, and then we rotate counterclockwise, right? So we have to keep rotating until we get to the second edge of the region. How do we find that? Well, that's whatever angle generates a value for the radius of 0. Of course, that means that cosine of 3 theta has to be equal to 0, which means that 3 theta has to be equal to pi over 2, and that means that theta is going to be equal to pi over 6. So this gives me the two limits of my integral. So the lower integral is going to be 0, the upper integral is going to be pi over 6. Now notice once again that as we're going from 0 to pi over 6, we're not going left to right, but we're rotating. We're imagining all these radii which sweep this region radially, just centered at the origin all the time and then rotating until we go from one position to the next. Okay? So now we have set up our limits. Now we have to figure out next what the integrand is. The integrand is simply the square of the radius. Alright, so we'll take our radius and we square it. Okay, and then times d theta. And that's it, folks. Okay, all we have to do now is just compute this integral, which hopefully is a familiar integral by now. If it is not, you may want to review the method for computing it, and that's it. Now, this is again a very basic example. In class, we're going to go through some more advanced ones, some of which can become a little bit tricky, especially when it comes to figuring out what the limits are. As you can tell, the integrand is r squared, and that's usually given, so the only difficulty will come out from figuring out what the limits of integration are.